So let's move on and take a look at that concept. What happens when the load case is not as nice and evenly distributed as before? And to do that, I want to bring in my same piece of the beam, which of course is a rigid beam and is also cut at an arbitrary distance. But in this case, I will now have the next more difficult load case, which would be a sloped line. So think of this here as WA, let's say, and then this here is the value WB, just indicating that we have different values on both sides, but in between they are actually linearly connected. So I have a linear slope here. And of course it comes out of a random space, out of some beam, so I cut it, and every time I cut it, I of course have to bring in my internal forces just so that you don't clinch when you look at these pictures. But at the end we are not worrying about these right now. However, I want to include them for completeness reasons so that we get used to this picture. And now I can apply my lengths here. So I want to let you know that this distance is once again just a random distance in the beam. So it's x in meters, for example. And we now have a linear sloped load case on there. So when could this be the case, by the way? So think of this as like a brick wall that increases from the left to the right. Or for example, this could be just the left side of a house where the roof slopes up, right? So you could have different load cases that actually represent a linearly sloped distribution. But my goal now is to think about what happens if I want to apply that load case to my shear force diagram. And to draw the shear force diagram, I start with my rigid body. And I start calling this the shear force. And the thing that I remember, right, is that here I now have a linear load case. And I also remember that minus W is equal to dV dx. And thanks to that formula, I can now extrapolate my knowledge from the previous section and understand that I can also take the load case and integrate to arrive at the shear force function. So now it becomes a little bit tricky because we have the minus here, but there's nothing that we can not solve. We can, however, use the similar logic and move from this sloped line to the shear force function here. And to do that, let's first indicate again that this is a cut system, and that now I have to end up with a parabolic function, right? Because again, here it's linear, the load case is linear, and I now need to end up with a parabolic function. And that parabolic function needs to reflect this slope. But now be very careful, because this slope here once again describes just the value of the slope of the shear force. So I say that again. This value here describes the slope of the shear force function at that location. To clarify that better, let's bring in our 3 or 4 distances again. So let's say here I have XA, then here I have XB, I have XC and XD. And maybe to better communicate that, let's change this up here to WD now, so that we understand that that relates to each other. But what I can do now is I can say that this value here relates to the slope of the shear force function. And so I have a small value there, and yeah, don't be fooled, it looks like it's positive, right, because we are above the dashed line, but keep this negative in mind. So sometimes when people see this negative, they just want to draw a negative function here, but it's the slope that is negative. So what does that mean? I have a negative slope that is not very large at xa. So I have something that is maybe like this. And then at xb, it's a little bit larger. So I'm actually drawing it a little bit steeper. And then at xc, it's very steep. So let's pretend that's right here. And then at xd, it's very, very steep. And so I actually now have my tangents, which let's say apply in this location here. And therefore I can now go ahead and draw my parabolic function. Hopefully I can do a good job here by hand to draw a parabolic function that goes through these tangents. And I think that's okay, at least it gets the point across. So hopefully that will help you to understand that we're really looking at this distance here and this distance and this distance as well as this distance, and we're looking at these values particularly to really describe the slope at a particular location. So this slope here, the one that is tangent to the function, is really described by the numerical value at this location xa. So the slope is defined, slope of shear function described by the value of the load case at particular location. So at location. And that is exactly why this slope here, for example, is steeper than the slope that I drew here, because we have a smaller value here and then a larger value here, and here a very large value. And again, be careful, because the minus here tells you that although you have a positive value here along these red axes, you will end up with a negative slope. So we now are ready to actually indicate our diagram and state that all of this here is really positive shear force, whereas this down here is a negative shear force. And this is just a symbolic representation, because we don't know what's going on here on the left, we don't know what's going on here on the right. We're just stating that due to the linear slope here, we would have a parabolic function that slopes, in this case, downward. And of course, we randomly let it go through 0 here. This could be different depending on what happens here and here. And so you hopefully understand that this entire shape could move all the way down, so that everything is a negative shear force. It could be completely up, so that everything is in positive shear force, or we can move this anywhere along this line, depending again on what happens here and here. However, when we move on to the moment now, this of course has a very important impact on the moment diagram, because you know that your moment is really the integration of the shear force. So let's highlight that one more time. So we integrate. And if we integrate, we know that at this location we must have a local maximum or minimum. So when we integrate the shear force function, then we go through 0 right here, and therefore we must have a maximum in our moment diagram. So let's go ahead and draw the free body diagram, or a cutout of that. And let's include that we now have to consider a local maximum or minimum. In this case, I'm very certain that it's a maximum for the very same reason that I used before. So it has to be a positive value here, because we have a force that pushes down on the beam, and therefore it makes the beam smile, which means that the reference fiber is in tension and the top of the beam is in compression. And therefore we must have a positive value here without a doubt, because there's no way that the beam could be frowning anywhere from here to here. So that leads us to the next conclusion, that here, everywhere along the part that we see here, we must have a positive moment. So I can already state that everything here must be positive without a doubt, because our reference fiber is in tension through and through. Now you may think, if I integrate a parabolic function, I of course end up with a cubic function, right? So you will find a cubic function here, and you might think, how do I now get to this cubic function if everything is positive? Don't my cubic functions usually look like this? So I'm going to erase this in a second because it's a very particular one, but a particular function, but you probably think of this cubic function right now that looks a little bit like this. And that is a cubic function, but this is a very specific cubic function, right? It's the cubic function that passes through 0 right here, but really what a cubic function tells you is that you have a possibility of 3 crossing with the x-axis. And therefore, you do not show this part of a function, or you could just show a small section of that, and you don't have to have this inflection point here. You can actually have a cubic function that is really represented by the values of the derivative. So for example, here at xa I have a value, at xb I have a value, and then at xc I have a value of 0, and then at xd I really have a value that is negative. And so that has to be represented now. And remember what we just learned or relearned or rediscussed, that the value here along those lines describes the slope of this function. So what does this mean? Here now I have a, be careful, positive value, right? It looks weird because we're going down here, but it's a positive value. So therefore everything to the left of this line has to be positively sloped. So what does that mean? That means I have a large positive slope here initially. So I have a large positive slope, let's say here. And then I have a little bit less of a slope. So that would be right here. And then I have a 0 slope. And then I'm going in the negative direction. And that is exactly the same logic that we used before. So now I can mark those tangent points. And I can go ahead and draw my cubic function, which may not look very different from a parabolic function, but trust me, I'm doing my best here to draw a parabolic function that is reflected now by those slopes. And let me indicate those slopes for you with the thick lines that I used before. So just so we understand that this here, of course, is one of those slopes. And then here I have the maximum where my tangent is 0. So now I think we can agree that the graph here on the right is very special case of a cubic function, and it does not always apply to our diagrams, because what we see here is a very specific case of a cubic function, and the way we actually get the slopes of that function is really through the shear force function. And therefore we now completed the cubic moment distribution for a non-evenly distributed load case. And this is a very simple load case. Before I talk more about that, let's just complete the diagram here, and let's agree that all of that is now in positive bending because the entire beam is smiling, as we discussed before. Now again, this is a very simple case of a non-evenly distributed force because we can describe it by a simple linear slope. So it's a linear function which then ends up in a shear force that is parabolic and a cubic moment. You may imagine that we can also make this more random, or we could, for example, make this a parabolic function that exists in real life. You can also make it a sine function or a cosine function, but the concept would remain the same. You would just integrate to get the shear force, and then you would, of course, pay attention to the negative here, but then you integrate further and get the moment. Now you may ask yourself, why am I emphasizing this so much, and why are we doing this here with a lot of emphasis in this class? And the reason is you will actually live off this as an engineer later on. And if you think this is challenging, please understand that you actually will take this further in the future. You can actually further integrate even the moment function to find more valuable information about this beam here. So you can further integrate and find, for example, the slope that this smiling beam will produce and the deflection. Let me visualize that for you, and let me make explicitly clear that this is actually not part of the lecture, which is why I'm going to put it below the page here. But I need you to know this so that you know, A, what you're in for when you go through your engineering career, and so that you understand why you want to pay attention to this topic so that you can later on apply the same knowledge. So when this beam here starts to smile, it actually produces a curvature of the smile, right? It can smile a lot or only a little bit. And so it turns out that if you actually integrate the moment, you can define the curvature. The way that engineers do that is really by this angle here. So let's call that theta, the angle to the horizontal direction. And so if you integrate your moment, you actually find the angle, and you can do that at every location, right? Just like we did it for every part along the axis for the moment and for the shear force. So you can find the angle that the beam has at a certain location. Now you may not fully agree with me that that is important to know, but you probably agree with me that the next thing is important to know, and that is when the beam deflects, it actually has a vertical displacement. So if I want to draw the smile of the beam, it probably would look something like this, let's say. So this is how much it would smile. And again, the angle here is really theta. So I'm going to mark this one more time for your reference. But what we really want is to know how much this deflects in this direction, right? So this we call delta. And that is something we can find by integrating the smile angle, or what I call theta here. And you can already see that where theta turns to 0, right? So if I would draw the tangent of that smile that is actually 0, of course I will end up with the maximum deflection, because where the angle is 0, and I integrate that 0 slope, I will find a maximum for the deflection, because I can really take this all the way down to find even my deflection. And why is that important? Because engineers often build critical structures where the deflection needs to be limited. For example, if you have ever noticed that the shopping malls have huge shopping windows, then you also have seen that there is a very long span length, and of course the longer the span is from left to right, the higher the deflection can be. So engineers need to ensure that this deflection does not get too large, so that the beam would actually push on the glass beneath it. So the glass really needs some breathing room because it's so brittle, and engineers have to make sure that the deflection value stays within certain limits and keeps some room between the glass and the beam. Likewise, every bridge and every building that you probably currently sitting in is limited in their deflection. The ceiling above you right now is limited so that the public feels safe in those structures and does not think, oh, this is bending or smiling too much. So the deflection for those structures needs to be limited. But let me make that one more time explicitly clear. Everything you see here below is really not part of the lecture. It was a good fit here to talk about it because we started to integrate from the load case to the shear force to the moment, and the next logical consequence would be to take it to these two levels. But that is something you will encounter in your future and in your engineering career. For now, I believe we can conclude this page and we understand how these functions relate to each other. We first started talking about self-weight or evenly distributed forces, and we saw that the shear force became linear and the moment became parabolic. Then we took it up a notch and talked about non-evenly distributed forces and the simplest case, which is a linear slope, so that we learned that we have a parabolic function that is produced for the shear force and a cubic function that is produced for the moment. And then in the future you will take it to even further levels. But I believe this is everything we need to know now, so we can actually conclude this and summarize this on the following page.